Morning, everybody. This is our lecture on section 1.7, and it is on linear independence and linear dependence. So consider a collection of vectors v1 up to vc in R. Okay, so in R-dimensional space, we have vectors v1 to vc, right? So each vector looks like that, right? And it's got whatever entries it has inside of it, but it's an n by 1 vector, column vector of a matrix, and we'll look at them as column vectors of matrices as well. So the linear combination. So, of course, 0 times v1 plus 0 times v2 all the way up to 0 times vc is equal to the 0 vector, right? However, are there other solutions to the vector equation x1 v1 x2 v2 plus xc vc equal to 0. So there's always just the 0 solution to this vector equation, or this homogeneous system of R linear equations and C unknowns. There's always the 0 solution. But, are there other solutions, right? I mean, there was always, of course, 3 situations that you get with linear systems. Either you get one solution. So if you get one solution, it's only the 0 solution in the homogeneous case. You get one solution, no solutions, or infinitely many solutions. Well, there's never no solutions because you always have the 0 solution. So it's either one solution or infinitely many solutions. So in other words, let's write that down. In other words, we are asking if the homogeneous EOUS system V1 VC 0 has either one solution, x equal to 0, or infinitely many solutions. Well, that's easy to tell when you reduce this guy, when you do your row operations to this guy, to reduce it to row echelon form. And either the solution has some free variables in it or it doesn't, right? So it's easy to tell as far as that goes. But we want to discuss this a little bit more in detail and develop some terminology here. So the definition is as follows. So vectors v1 to vc and R are linearly independent when the only solution to that system v1 vc is x equal to 0. And v1 to VC in R are linearly dependent when there are infinitely many solutions. To that same system. Okay, and it's never the case that there's not a solution, right? Because the system is homogeneous, so x equal to 0 is always a solution. All right. So, for example, so are the following vectors linearly independent or dependent? And I've got vectors 1, minus 1, 0, 0. 0, 1, minus 2, 0. 0, 0, 1, minus 3. And minus 1/6, 0, 0, 1. And so I've got these four vectors here, and I'm asking, are they linearly independent or linearly dependent? So we look at the associated homogeneous system of equations, or the vector equation, x1, v1, x2, v2, x3, v3, x4, v4, summing to 0. Right? And we try to see if there's one solution or infinitely many solutions. So let's proceed with that. Oops. 1 minus 3 minus 1/6, 0, 0, 1, and then all these are equal to 0, 0, 0, 0. Okay, so I'm going to do my row operations here. So I'm going to add row 1 to row 2. So that's 0, 1, 0, minus 1/6. And then 0, minus 2, 1, 0, 0, 0, minus 3, 1. Okay, I'm going to add row 2 to row 3 twice. So it's going to be 1, 0, 0, minus 1/6. And 0, 1, 0, minus 1/6. 0, and add 2, you get 0. Add 0, stays 1. And then add negative 1/6 twice, I get negative 1/3. These are all 0. So, I mean, by the way, you don't actually have to write this last column of zeros. I mean, as you notice, I mean, it just stays 0 all the way. So it's not like the non-homogeneous system, right? With a non-homogeneous system, you have to keep track of that last column because things change as you start doing row operations. These guys add together and numbers change and so on and so forth. But here they don't. They just stay 0. But if you like, you can leave it there too. Add row 3 to row 4 3 times. 1, 0, minus 1/6, 0, 0, 1, minus 1/3, and now we got 0, 0, 0. Add this 3 times, and we get 0. Right, so my leading coefficients are in these columns, all right, and my leading coefficients or pivots, right? So the book has two words. Well, they use pivot more, so I like leading coefficients. But anyway, your leading coefficients are in columns 1, 2, and 3, right? Going strictly to the right. And column 4 doesn't have a pivot, right? So that means x4 is the free variable, right? So in a solution, to this system, right? So there's infinitely many solutions. There are infinitely many solutions to, right, that original system. So let's write it as vectors this time around. As a vector equation rather than as a matrix equation. Right, so those are fine. Just move this guy over. All right. So there's infinitely many solutions to this. So that means it's linearly dependent. So vectors are linearly dependent. All right. So notice that oh, by the way, what would be a solution to this other than the trivial solution? Why don't we actually like write one of those down, right? I mean, if we had, say, like x4 is free, x3 is then equal to 1/3 x4, x4 or x2 would be equal to 1/6 x4, and x1 is equal to 1/6 x4, right? So that would be a solution to this system of equations, or this vector equation. So some particular solution to this homogeneous system would be so for example, right, x1, x2, x3, x4 equal to, and let's pick an example, we'll say x4 is equal to 6. So if x4 is equal to 6, then x1 and x2 are both 1, and x3 is 2, right? So 1, 1, 2, 6. Right, so if this is 1, 1, 2, 6, right, the first row gives you 1, minus 1, 0. Second row gives you 1, minus 1, plus 0, plus 0, 0. Third row is 0, minus 2, plus 2, 0, 0. Fourth row, 0, 0, minus 6, plus 6 is 0, right? So there is a there is a solution to that homogeneous system other than the 0 solution. All right. So here's a theorem. So we're going to be a little bit more sort of this class is a little bit sort of more theoretical than a little bit more abstract than your typical calculus course. So I'm going to write a theorem and do a proof. And, try to follow along with that. Start learning how to do mathematical logical proofs. It's definitely a good exercise for you and give you more of a handle on the subject. Okay, so vectors v1, v2, up to vc are linearly dependent if and only if one of these vectors, some vi, is in the span of the remaining vectors. v1, vi minus 1, vi plus 1, vc. All right. So linearly dependent means one of the vectors is in the span of the remaining vectors. So let's do a proof of this fact. And remember, the span is the set of linear combinations of these vectors. In other words, these guys are linearly dependent if one vector is a linear combination of the rest. Right? If one vector is a linear combination of the rest. Proof. So if v1 to vc are linearly dependent, then there is x1, x2, xc not equal to 0, 0, 0, right? Not the zero vector, such that x1 v1 plus x2 v2 plus xc vc is equal to 0 vector. So if they are linearly dependent, there is a non-zero solution to, there's always the zero solution, but, when you're linearly dependent, you also have some non-zero solution to this vector equation, or this associated linear system of linear equations, or whatever. All right, so one of these guys isn't zero. So, this vector is not zero. Of course, this vector is not equal to 0, 0, 0, 0, right? The vector is not zero, but it doesn't mean that, not part of it is zero. Part of it could very well be zero, just there is some part that isn't. There's some part of that vector that isn't, x1 to xc. So without loss of generality, say that x1 is not zero. It doesn't have to be, but then again, if it wasn't, something in here, one of these guys isn't zero, so I can bring it to the front and renumber. Right? I can take the non-zero guy, put it up front, and switch the numbers on these vectors, and then x1 is not equal to 0. So it doesn't really matter. And that's what I mean without loss of generality, because if it was that x1 is equal to 0, I could switch x1 and v1 with some other vector in the middle that doesn't have a 0 coefficient, and then x1 is not 0. Okay, so without loss of generality, say that x1 is not equal to 0. Therefore, x2 v2 plus xc vc is equal to minus x1 v1. So divide by that, And that's why we needed that x1 wasn't 0, because otherwise I can't divide, right? You can't divide by 0. Plus, but minus. I could put plus. Minus xc over x1 vc is equal to v1, right? So I have that v1 is a linear combination of v2 to vc. So v1 is in the span of v2 to vc, right, which is what we wanted to show. All right, so that's half the proof. Okay, the statement of the theorem, you'll notice it says if and only if. So vectors v1 to vc are linearly independent if and only if some vi is in the span of these guys here. So that means if these are linearly dependent, then one vector is in the span of the rest. Also, it means if one vector is in the span of the rest, then the vectors are linearly dependent. So if and only if. Logically equivalent. So there's two parts to the proof. There's one direction. If the vectors are linearly dependent, then one vector is in the span of the rest. Now, assume that v1 is in the span of v2 to vc. Right, so there are real numbers, x2 to xc, such that v1 is equal to x2 v2 plus xc vc. So I could just move this guy over here. 0 is equal to minus v1 plus x2 v2 plus xc vc. And so since minus 1 is not equal to 0, right, there is a non-zero solution to this system of linear equations, v1 up to vc equal to 0. So v1 to vc are linearly dependent. Okay, so why is that statement important? What does it say? It says if we have a set of linearly dependent vectors, well, we can throw away vectors that are linear combinations of the other until we reach a linearly independent subset. So one consequence of this theorem is that if v1 to vc are linearly dependent, then we can remove one vector that is a linear combination of the rest. Of the remaining vectors, and check for independence dependence again. And then we repeat this process until we reach a linearly independent subset of V1 to Vc of largest possible size. Right? I mean, you got so many vectors. Say we got 6 vectors. So you got 6 vectors, and you ask, well, linearly independent or dependent? Well, dependent. V3 is a linear combination of the rest, so we throw it away. Now we got V1, 2, 4, 5, 6. Linearly dependent or independent? Well, say it's dependent. And V6 is a linear combination of the rest, so we throw away V6. And now we're left with 4 vectors, V1, 2, 4, 5. Linearly independent or dependent? Oh, it's independent this time. Okay, you just keep, peeling away vectors until you get an independent subset. Now, how do you do that? Now, in practice, it's actually easier to do than what I described here, but this is the theoretical idea behind it. So to do this in practice, simply take a matrix consisting of the vectors reduced to row echelon form, and take the columns that are pivot columns. Right? The columns that aren't pivot columns, those are the ones that are responsible for making those free variables there. So if we chuck those guys out, then we're good to go. What's left over, every column is a pivot column, so it's a linearly independent subset. Take the columns that are pivot columns, and this is your independent maximal linearly independent subset. Okay, one caveat about this that I'll mention as we go along here. Okay, so for example, find a maximal linearly independent subset of the columns of the following matrix. Okay, so here's the matrix. Column 1, -1, 0, 0, 1, 0, -1, 0, 1, 0, 0, -1, 0, 1, -1, 0, and 0, 0, 1, -1, no, 0, 0, 1, 0, -1. and 0, 0, 1, minus 1. I made that really ugly. Let me do it again. So I've got 6 columns here. I know what the pattern is I'm looking for here. 0, 1, negative 1, 0, 0, 1, 0, minus 1, 0, 0, 1, minus 1. Okay. So I want to get this into row echelon form. Okay. So first I'm going to add row 1. By the way, notice that I don't have this here. Okay, I don't have that column there. I mean, we're just looking at the vectors themselves. This column, you don't have to really keep track of it. So we're just going to leave it out this time around. You can put it in if you want, but I just want you to be aware that I'm actually not using it here. All right, so I'm going to add row 1 to row 2. So this is 1, 1, 1, 0, 0, 0. 0, 1, 1, 1, 1, 0. 0, minus 1, 0, minus 1. 0, 1, 0, 0, minus 1, 0, minus 1, minus 1. Now I'm going to add row 2 to row 3. So I got 1, 1, 1, 0, 0, 0. 0, 1, 1, 1, 1, 0. And then 0, 0, 1, 0, 1, 1. Right? 0, 1, 0, 1, 1. And then I'm left on the bottom here with 0, 0, minus 1, 0, minus 1, minus 1. And now add row 3 to row 4. And I get all zeros. So where are the pivots? Okay, so pivot columns are 1, 2, and 3. All right, pivot columns are 1, 2, 3. So where is my linearly independent set of vectors? It's not these. Okay, these are a linearly independent set of vectors, true. These 3 column vectors here. They are linearly independent, but they're not the original vectors I started with. Okay, what I want are the original vectors I started with. Which subset of those is linearly independent? Okay, so pivot columns are 1, 2, and 3. So these are linearly independent. So maximal linearly independent subset. Okay, so there it is. So my maximal linearly independent subset of the original column vectors are, well, those right there. Right? The question is which subset of these vectors is linearly independent. So you do the row reduction just to see where the pivots are. So we get it down to row echelon form. Here are the pivots. Column 1, 2, 3. Okay, column 1, 2, 3. So those columns of the original matrix are a maximal linearly independent subset. There are other ones besides those, but but these will do. Right, so you've got this vector, this vector. Let me do that a little better. Should know what those vectors are. Alright, so it's 1, minus 1, 0, 0. 1, 0, minus 1, 0. And 1, 0, 0, minus 1. This is column 1. Column 2. Column 3. Okay? Alright. A few miscellaneous facts just to end off with here. Okay, one, if so the set of vectors zero v2 up to vc is always linearly dependent. If you're talking about a set of vectors and one of those vectors is 0, it's always linearly dependent. Why? Because, I mean, there's always a solution to the vector equation equal to 0. Right? Because I could put whatever I want in front of the 0 vector, so 3 times 0 plus all of these guys are 0 is equal to 0. So again, the solution is not the 0 solution. Even though most of the entries are 0, one of them isn't. Right? So the solution is 3, 0, 0, 0, 0, which is not equal to the 0 vector. Right? The 0 vector is 0 everywhere. A non-zero vector is not 0 somewhere. Not everywhere, somewhere. Alright, so anytime you have the 0 vector, you're automatically linearly dependent, and of course, that could be the first one that you throw away in trying to find a linearly independent subset. Two vectors, non-zero vectors, v1 and v2, are linearly dependent if and only if v1 is equal to k v2 for some k. That is, v1 and v2 are parallel. Alright, so one vector is a linear combination of the rest. Well, a linear combination of one vector is just a scalar multiple of that vector. So here's like v1 and v2 looking like this. Alright, so this is v1, and we can make v2 face in the other direction. v2, like that, linearly dependent. And then if you had them not parallel, v1, v2, these are independent. Okay, so two vectors are linearly independent if and only if they're not parallel, or linearly dependent if and only if they're parallel. Okay, all right, that's the lecture for this section.